Let's do another example of this. I was going to let everyone try this, but I think it's better if we do it together. Here, let me go to this slide. I'll post the notes as well. But let's say, for instance, we had this. Oh, sorry. Let's say we had this function here. Okay. The first one here. Okay, so this is our exponential function, right? Okay. The initial value then would be 615. Okay, that's the number in front. Okay. Not to mention, if you replace x by 0, you would get 615. We have growth here. This is an exponential growth then. Now, how do I know that? Because this base here is 1.25, greater than 1. And by what rate is it growing? By what rate? When they ask for rate, you want to get that r. And just like on the previous slide, since here, this is greater than 1, we must have 1 plus r here, equal to 1.25. Okay, then it's just like over here, just like the same kind of calculation, you subtract 1, and your r is 0.25. So we get r is 0.25. So the rate, the percent that it's growing is 25%. So this is exponential growth, and the function values are growing at a constant percent rate of 25%. I mean, you could also just say the rate as a decimal is 0.25. Whereas in the second one here, we have 300, right? Okay, so that's the initial value. We still have growth here because this base is 1.09 greater than 1. Okay. So in this case, okay, we have growth. The initial value is 300. Okay, but what is the rate? What is r, in other words? Well, again, since it's growing, we must have 1 plus r equal to 1.09. So r has to be 0.09, just basic calculation. So the rate is 0.09, and as a percentage, it's 9%. So the function values are growing at a rate of 9%. Down here, it's a little bit different, though. Now, why is this different? Well, we have 3,900. That's the initial value, right? That's the number in front. It's decaying because if you notice here, it's 0.95. 0.95. Less than 1. So that's why it's decaying. Okay, so what's r going to be? Well, what's the rate? Well, we have to have r as 1 minus r is 0.95. That's what I was trying to show here. When it's less than 1, we have to have 1 minus r. Now, how do you get r? Well, it's really just this kind of calculation. It's basically this kind of calculation. Instead of 0.85, you would have 0.95. And you get 0.05. So the function values here, they're decreasing at a percent. They're decreasing by 5%. That's 0.05 as a percent. These two are easy. It's just this one we have 0.11, but it's decaying. Here we have 0.11 also, but it's growing. And here the initial value is 1,000. Here the initial value is 1,200. Okay. All right. And finally, for this one, we have 400 as the initial value. This is decaying, okay? We have decay. And why is that? It's less than 1. So we have to figure out r. Well, 1 minus r then is 0.55. Since it's decaying, we have to have this. And what's r? Well, again, you just solve for r algebraically. We get r is 1 minus 0.55, which is 0.45. But that's the same as 45%. So here the function values are decreasing by 45% if you increase x by 1. That's what's happening here. So this table I was going to have everyone fill in, but again, we're getting low on time. I will post the, I mean, I'm not done yet today, but I will post the notes as well. But here's another example. So if we look at these function values, right, we have f of x is this, okay? But notice again, this is decreasing, right? And how do I know that? Well, the base here is 0.25, which is less than 1. Being less than 1, it has to be decreasing. And how do we get our r? Well, again, that's what I'm doing here, right? Basically here we have 0.25 is 1 minus r. So you just algebraically solve. I mean, essentially you're just going to add r to both sides and subtract 0.25. You get r is 0.75. That's the decay rate, which again means the function values are decreasing at a rate of 75%. I mean, here I just put some function values in to confirm that. And then we did these calculations. This is the percent, the percent change in the function values. That's what we have here. You know, again, f of x, when x is 0, the initial value, which is here, we get 10. When x is 1, we get 2.5.
I have a question.
Okay.
Can you go back? Why is it that for the fourth to last, the decay of 0.05, I mean 0.05, the number went from 95 to 5. However, in the next one, when you subtract it by 1, wouldn't the 11 become 0.01?
No, here we already have 1 minus. That's why. Here we don't have that.
Oh.
That's why. Okay.
Okay.
Awesome question.
So if it's the number stays the same always?
Exactly.
Okay.
I mean, essentially because you want to figure out what that rate r is. But if it's 1 minus something, this something has to be r, or 1 plus something.
Okay, thank you.
Okay. Okay. All right. Let me see what time is it. That's a great question. But let me see, how much time do we have left? Because we have like 40 seconds. But I wanted to present this. So what's probably going to, I know this stuff is not easy. So what I am expecting to do is I'm probably going to do a lot more examples of this. Not like just this one, though. But we'll do some word problems because I think that will help us understand this better. Because I know this stuff's not easy. I know it's a little weird, but exponential functions are very important. I mean, you'll see in the word problems we do next time, they do come up, for instance, in half-life and radioactive decay, and they can also be used with population growth. And there, basically, what's going to happen from the word problems are you're basically going to figure out what the exponential function has to be, and then you'll be able to calculate certain values. Okay? I mean, I know this stuff's not easy, but again, don't give up on me. This is hard stuff, but it's not supposed to be easy, okay? Again, this is just a function that's changing at a constant percent rate. So, you know, the function values are increasing or decreasing by 1%. So, all right, we're going to have to stop here. We'll pick up from here next time on Friday. Okay, again, this is not on the first test. Don't worry. Okay, well.